Greetings, everybody. Learning is a hobby here. I want to go over my summary for Chapter 4 in Topics in Commutative Ring Theory by John J. Watkins. The notes, the PDF for my notes are already up on the Patreon page if you want to check those out. Let's go through my notes here. I'll bring them up and we'll just go through them. And while I'm doing that, let me just say there's a lot of interesting historical information in this chapter, mainly about set theory, the history of set theory. So I definitely recommend reading the last couple pages of, you should read the whole chapter, obviously, but particularly if you're interested in some of the history, check out the last two pages of this chapter because he gives a lot of background information, for example, on the axiom of choice and Zorn's lemma and so on, which is interesting. So, but anyway, I didn't write that down here in the notes because, of course, my notes are just bare bones bullet points, kind of like the main ideas of the chapter. So, you should, as always, you should always read the chapter yourself. Anyway, let's go ahead and get into this. So, the primary goal of this chapter is to show that every ring has a maximal ideal. All right, this fact will require the use of Zorn's lemma, which we'll actually talk about in a few minutes. Zorn's lemma is one of the indispensable tools for the modern mathematician. So it's important to know what it is and how to apply it. And we'll apply it for the main goal of this chapter in a few minutes. All right, in order to state and use Zorn's lemma, we need to make precise exactly how we compare things, which leads us to definition 4.1. Excuse me. A partial order on a set S is a relation on S, which is satisfies these three axioms here. It has to be reflexive. In other words, for all x and s, x is less than or equal to x. This less than or equal, by the way, is not necessarily the usual less than or equal that we think about, when we talk about real numbers or integers or things like that. This is a abstract relation here. We call it a partial order um, if it satisfies these three properties here, right? Two, it has to be anti-symmetric, meaning that for all x, y in S, x less than or equal to y and y less than or equal to x implies that x is equal to y. And three, it has to be transitive, meaning that for all x, y, z in S, x less than or equal to y and y less than or equal to z implies that x is less than or equal to z. All right, whenever we have a partial order on a, sorry, whenever a partial order on a given set seems to be the most natural one, we'll call it the standard partial order. So if we say that, it's sort of like the most natural one that should come to your head. Let's look at a few examples. Example one, if S is the set of integers, then we define the standard partial order on S as follows: x less than or equal to y if and only if y minus x is non-negative. We use the same definition for the standard partial order on real numbers and rationals as well. We looked at these types of orders when we looked at our construction of the real numbers and everything. The proof that examples 1 through 4 are indeed partial orders is left to the reader. He doesn't do it in the book, so we'll do it here like we're supposed to. So let's show that this is a partial order on the integers. So maybe I won't belabor it, but obviously, x minus x is 0, so x is less than or equal to x. 2x less than or equal to y less than or equal to x implies y minus x greater than or equal to 0, and x minus y greater than or equal to 0 implies x minus y greater than or equal to 0, and minus x minus y greater than or equal to 0. Therefore, x minus y is 0 by the trichotomy of the integers, which implies that x is y. And then finally, transitivity, x less than or equal to y less than or equal to z implies y minus x greater than or equal to 0, z minus y greater than or equal to 0, which means that their sum is greater than or equal to 0. And if you just simplify the left-hand side, you find that z minus x is greater than or equal to 0, which means that x is less than or equal to z. So it's a partial order on the integers. Right? Example 2, let S be a collection of sets. We define the standard partial order on S as follows, where A, B are sets in the set S. A less than or equal to B if and only if A is a subset of B. And like I said, I won't belabor this. If you want to, read through this in detail, you can look. You just have to show that it satisfies the three conditions. So I won't go through this in detail because it's very similar to what we just did, but you can pause your screen and look at this if you want to. Right. Example 3 is very similar to the to the second example. Let S be a collection of sets. This time we will define another quite natural order on S called reverse inclusion as follows, where A, B are sets in the set S, A less than or equal to B if and only if contains B, or A is a superset of B. Um, the proof I skipped because it's extremely similar to the one I just did in example 2, but you should try it yourself, et cetera, et cetera. Then finally, example 4. Let S be the set C of R, which is the set of continuous real-valued functions on the real line. We define the standard partial order on S as follows, where F, G are functions in S. We say that F is less than or equal to G if and only if F of X is less than or equal to G of X for all X in the real numbers. Right. And again, I won't belabor the point here. You could pause your screen and look at the verification of the 3 axioms here to show that this is indeed a partial order on the set of continuous real valued functions. Okay, just a note uh, that a set equipped with a partial order may not have the property that every pair of elements are comparable. That's why we call it a partial order. If every element in the set is comparable, then we call the partial order, we actually call it a total order. So that's definition 4.2. A partial order on a set S is a total order or a linear order if for any x, y, and s, either x is less than or equal to y, or y is less than or equal to x. In particular, if less than or equal is a partial order on a set S and C is a subset of S, then we say that C is a chain if the partial order is a total order on C. All right, here's some examples of totally ordered sets. The standard order on R is a total order. This means that any subset of R is a chain. Example 6, let S be a set with the standard partial order given by inclusion, meaning the order that we talked about in example 2. So let A1, A2, A3, et cetera, be subsets of S. Then the set C, where so here we have listing a sequence here of unions of the sets from the set S: A1, A1 union A2, A1 union A2, union A3, et cetera. Obviously, C is a chain. In other words, they're all the ones from the left are all included, as you go to the right. This is an example of an ascending chain, and here in example 7, we have an example of a descending chain. Right, let's the C of the closed interval from 0 to 1 be the set of all continuous real valued functions on the closed interval from 0 to 1 with the standard partial order given in example 4. Then the set of functions less than or equal to x cubed, less than or equal to x squared, less than or equal to x is a descending chain. Remember here, we're only looking at input values from the closed interval from 0 to 1. It's not true if you widen that set, not necessarily. Um, so that's an example of a descending chain. All right, here's another note. We'll often write descending chains like the one above in the other direction, just so that we can, the we can list the to the right of the ordering. All right, chains need not be countable. For example, R minus Q is an uncountable chain in R. Right here we get we need a couple more definitions before we can get to Zorn's lemma. Definition 4.3 says let less than or equal be a partial order on a set S. Let A be a subset of S. An upper bound of the set A is an element S in S, such that A is less than or equal to S for all A in A. We've actually seen this definition of upper bound before in analysis, so hopefully this is familiar. Then we get a definition of maximal element. So let less than or equal be a partial order on a set S. An element M in S is a maximal element of S if there's no element S in S, S not M, such that M is less than or equal to S. So slightly different, we mean something slightly different between maximal element and upper bound. So you got to be careful about the details. All right, and now we have enough background that we can state Zorn's lemma, which is theorem 4.1. Let less than or equal be a partial order on a non-empty set S. If every chain in S has an upper bound in S, then S contains a maximal element. Now, it says lemma here when we're stating this as the theorem, so we should prove it, but I'll hold off, and the book does too, on talking about the proof of Zorn's lemma until after we prove theorem 4.2. So let's do that first. We're going to use Zorn's lemma in the proof here. All right, so this is the main point of this chapter. Theorem 4.2 says every non-zero ring has at least one maximal ideal. And here's the proof. Okay, so let R be a non-zero ring, and let S be the set of proper ideals of R equipped with the partial order of set inclusion. Then S is not empty since the zero ideal is an element of S. So then what we'll do is we'll take a chain C in S and let the U be the union of all the ideals in the chain C. Then for any I in C, any ideal in the chain C, I is an element of U, right? Because it's the union of all the elements in the chain. Then we want to show first that U is also an ideal of the ring R. So let A and B be elements of U, then A is in I, B is in J for some ideals I, J, and C. Either I is a subset of J or J is a subset of I, since C is a chain. And so without loss of generality, we can assume I is a subset of J. Then A is an element of I, implies A is an element of J. And since J is an ideal, A minus B is in J. And since J is part of the union that was used to make up the set U, that means that A minus B is an element of U. So U is closed under addition. In other words, it's the additive structure is an abelian group. Right? Property two, it has to absorb also multiplication from the bigger ring. Remember, that's the second property of an ideal. Let A and U, R and R, then A is an element of I for some I in C, then that implies that RA is an element of I since I is an ideal, which implies that RA is an element of U since I is a subset of U, right? All right, and one, one and two taken together show that U is an ideal of R. So now we just have to make sure that U is a proper ideal of R, and then Zorn's lemma will give us what we want. So lastly, if one is an element of U, then by one here, again, we're talking about the abstract entity one, meaning the multiplicative identity, not necessarily the number one, right? So lastly, one an element of U, then one is an element of I for some I in C, which contradicts that I is an element of S. Remember, S is the set of all proper ideals of R. Therefore, one is not an element of U, which implies that U is an S. So U is a proper ideal of R. Therefore, U is an upper bound for C in S. U is an element of S, and C was an arbitrary chain. Therefore, every chain in S has an upper bound in S. So by Zorn's lemma, S has a maximal element. And since S is the set of all proper subsets of the non-zero ring R, that means that R has at least one maximal ideal, and that's the proof. Okay, we still don't have a way of constructing maximal ideals. Remember, from the proof that we just talked about, U is simply an upper bound for C and need not itself be a maximal ideal. However, we know maximal ideals exist in any non-zero ring by the theorem we just proved. And just a bit of advice here that the author gives us, the key to successful use of Zorn's lemma is making appropriate choices for the set S in the partial order. Okay, and now we get back to the discussion here that I referred to when we didn't prove Zorn's lemma. So Zorn's lemma is actually equivalent to the following two theorems here, or axioms, I guess you could call them. Zorn's lemma is equivalent to the axiom of choice, which says this: let S lambda be a non-empty set for each lambda in an index set capital lambda. Then there's a function f defined on the set capital lambda, such that f of lambda is an element of S lambda for each lambda in capital lambda. So in other words, they're saying for any collection of sets, there's a choice function. This is called an axiom because it's not proven, it's assumed usually, but particularly when you're dealing with Zermelo-Fraenkel set theory, which we talked a little bit about when we were going through Tao's book in Analysis 1. We will get to the axiom of choice in Tao's book. So not only does the author not prove the equivalence of Zorn's lemma and the axiom of choice or the well ordering principle, which I'll talk about in a minute, um, none of these things are proven here, but I'm assuming that when we get to, I think it's chapter 8 in Tao's analysis 1, we'll talk about the axiom of choice, and we might get more in detail about the axiom of choice there. If not, I do plan on, having a series on set theory proper on the channel after we get through my sort of playlist on elementary logic, so that we will study this in detail at some point in the future. So here, since the book here doesn't go in detail into it, I won't do that either. So that's the axiom of choice. There is also the well ordering principle. Before we talk about that, though, let's remind ourselves what we mean by well ordering. So a set is said to be well ordered if we can give it a total order such that every non-empty subset has a least element, and this is the well ordering principle. It turns out that any set can be well ordered. Okay, and now the last thing I'll talk about here is that these three statements here, Zorn's lemma, the axiom of choice, and the well ordering principle, are actually all equivalent to each other, meaning that if you assume one, you can prove the other two. So usually for Zermelo-Fraenkel set theory, we assume the axiom of choice, but not always. But that seems to be like sort of the standard environment that modern mathematicians choose to work in. Anyway, that's the end of chapter 4. Kind of a short chapter. But again, just to remind you, don't skip the historical info at the end. It's kind of interesting. I'm not going to talk about that here though, because again, this is just my notes on the chapter. Okay, so I'll be working on the exercise set here for chapter 4. There's a small number of problems here. It's not very long at all. There are 6 problems, so hopefully I'll be able to get that out soon. I'm still working on Niven's section 1 point exercise set for section 1.3. I'll be getting that out as soon as I can, as well as all the other stuff I'm working on. Let me know what you guys think down below, and I'll see you in the next video.